The largest motor load is often excluded from residential electrical calculation examples because it is considered a constant load. A constant load is an electrical load that operates continuously or for extended periods at a consistent power level. Examples of constant loads in a residence include refrigerators, freezers, water heaters, and HVAC systems when they are actively heating or cooling. Because constant loads operate predictably, their energy consumption can be estimated and accounted for separately from other intermittent loads. When performing residential electrical load calculations, the primary goal is often to determine the minimum service capacity required to safely and reliably supply power to the home. This involves calculating the total demand load, which is the sum of all continuous and non-continuous loads. Continuous loads, defined as loads that operate for 3 hours or more at a time, are typically factored in at 125% of their rated current, as per the National Electrical Code, or NEC. Non-continuous loads are factored in at 100% of their rated current. The largest motor load, if considered a constant load, is already accounted for in the overall demand calculation based on its continuous operation. Including it again as a separate load would result in double counting its power consumption. Furthermore, the impact of a constant motor load on the overall energy consumption of the home is relatively stable and predictable. It does not introduce significant fluctuations in the total demand load, which are more concerning when sizing the electrical service. Other intermittent loads, such as lighting, small appliances, and plug-in devices, can vary significantly depending on usage patterns. These fluctuating loads are more critical to consider when calculating the total demand load and ensuring that the electrical service can handle peak demand period. In contrast, a constant motor load contributes a steady baseline load that does not significantly impact peak demand. Therefore, the focus is on accurately assessing the fluctuating loads to determine the appropriate service capacity. Consider a home with a refrigerator that operates continuously and a central air conditioning system that runs for extended periods during the summer months. These constant loads contribute a significant portion of the home's total energy consumption. The electrical load calculation would account for these loads by factoring in their continuous current draw at 125%. However, the calculation would also need to consider intermittent loads, such as lighting, appliances, and electronic devices, which may vary depending on usage patterns. By excluding the largest constant motor load as a separate item, the focus remains on accurately assessing the impact of fluctuating loads on the overall demand. This helps ensure that the electrical service is adequately sized to handle peak demand periods without being oversized unnecessarily. To understand the concept of constant loads in residential electrical systems, it is important to differentiate them from non-constant loads. Non-constant loads are electrical loads that operate intermittently or for short periods, with varying power consumption levels. Examples of non-constant loads include lighting fixtures, small appliances, power tools, and electronic devices. These loads are typically switched on and off as needed, and their power consumption depends on their usage pattern. When performing residential electrical load calculations, non-constant loads are factored in at 100% of their rated current. However, it is important to consider the diversity factor, which is the ratio of the maximum demand of a group of loads to the sum of their individual ratings. The diversity factor accounts for the fact that not all non-constant loads will operate simultaneously at their maximum power levels. By applying the diversity factor, the calculated demand load can be reduced to a more realistic value, preventing the electrical service from being oversized. In contrast, constant loads are typically factored in at 125% of their rated current, as per the NEC. This is because constant loads operate continuously or for extended periods, and their current draw is relatively stable. The 125% factor provides a safety margin to account for potential variations in voltage or temperature, as well as any inefficiencies in the electrical system. By using different factors for constant and non-constant loads, the electrical load calculation can accurately reflect the actual demand on the electrical service. This helps ensure that the electrical service is adequately sized to handle the expected load without being oversized unnecessarily. When calculating the total demand load for a residence, it is important to consider all applicable factors and adjustments. These factors can include the general lighting load, appliance load, heating and cooling load, and any special loads, such as electric vehicle chargers or backup generators. The general lighting load is typically calculated based on the square footage of the home, as per the NEC. The appliance load includes the power consumption of all major appliances, such as refrigerators, freezers, washing machines, and dryers. The heating and cooling load depends on the type of heating and cooling system used in the home, as well as the climate conditions in the area. Special loads, such as electric vehicle chargers or backup generators, may require additional calculations and considerations. By carefully considering all applicable factors and adjustments, the total demand load can be accurately calculated, ensuring that the electrical service is adequately sized to meet the needs of the home. In addition to calculating the total demand load, it is also important to consider the voltage drop in the electrical system. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause appliances and equipment to operate inefficiently or malfunction, and it can also reduce the lifespan of electrical components. The NEC specifies the maximum allowable voltage drop for different types of circuits. For example, branch circuits are typically limited to a 3% voltage drop, while feeder circuits are limited to a 5% voltage drop. To minimize voltage drop, it is important to use conductors of adequate size and to keep circuit lengths as short as possible. Voltage drop can be calculated using Ohm's law, which states that voltage drop is equal to the current multiplied by the resistance of the conductor. By carefully considering voltage drop and taking appropriate measures to minimize it, the performance and reliability of the electrical system can be improved. Another important consideration in residential electrical systems is grounding and bonding. Grounding is the process of connecting the electrical system to the earth, while bonding is the process of connecting all metal parts of the electrical system together. Grounding and bonding provide a low impedance path for fault current to flow back to the source, which helps to protect people from electric shock and prevent fires. The NEC specifies the requirements for grounding and bonding in residential electrical systems. These requirements include the use of grounding electrodes, grounding conductors, and bonding jumpers. By following the NEC requirements for grounding and bonding, the safety and reliability of the electrical system can be enhanced. Furthermore, surge protection is an important aspect of residential electrical systems. Surges are sudden increases in voltage that can damage or destroy electronic equipment. Surges can be caused by lightning strikes, power outages, or switching operations. Surge protection devices, or SPDs, are designed to protect electronic equipment from surges by diverting excess voltage to ground. SPD are available in various types and sizes, and they can be installed at the service entrance or at individual branch circuits. The NEC recommends the use of SPD in residential electrical systems to protect sensitive electronic equipment such as computers, televisions, and appliances. By installing SPD, the risk of damage from surges can be significantly reduced. In summary, residential electrical load calculations are essential for determining the minimum service capacity required to safely and reliably supply power to a home. The largest motor load is often excluded from these calculations because it is considered a constant load, and its energy consumption is already accounted for in the overall demand calculation. When performing residential electrical load calculations, it is important to consider all applicable factors and adjustments, including the general lighting load, appliance load, heating and cooling load, and any special loads. Additionally, voltage drop, grounding and bonding, and surge protection should be carefully considered to ensure the safety and reliability of the electrical system. By following these guidelines, residential electrical systems can be designed and installed to meet the needs of the home while providing a safe and reliable source of power. Consider the NEC tables 220.11, 220.12, 220.53 and others. These are critical in sizing the electrical service.